If by breath alone I can be a bigger man, how ephemeral. All right, so a little bit of the history. I had mentioned before that Galen didn't quite have the plumbing correct, perfectly mapped out in the chest. He had divined some of the mistakes made by Aristotle, but he wasn't willing to completely turn over the apple cart. And he still subscribed to Galen's idea or Aristotle's idea of the four elements, earth, air, fire, and water, and that the human was some sort of complex combination of those three things. And thus, he thought that the element of coolness coming from air, the element of coolness was introduced into the body by the breath. And this was something that was constantly required to temper the heat of the heart. So the heart was that source of fire in the body, and the lungs were there to temper that and cool, which is why you could not live without air. And so Leonardo da Vinci did a much more careful analysis of the lungs, and he played around with the tissue, describing it as dilatable, meaning expandable, and extensible, like the tinder made from a fungus. Has anybody ever played with moss or like that, like a spongy kind of lichen? He's sort of describing it as like that. But it is spongy as if you press it, and if you press it, it yields to the force which compresses it. And if the force is removed, it increases again to its original size. So he's observing that it's able to change volume, really. It's able to change shape and volume, which is heading towards an understanding of the lung's actual function. Then there was this guy, William Harvey. I had sort of flashed past Harvey in a past lecture, but here he is now. And Harvey was the first person to understand that there was some sort of nourishment that the body gained that was conveyed via the blood, but was essentially provided by the lungs. So what did he say? Quote, "Life and respiration are complementary. There is nothing living which does not breathe, nor anything which is breathing which does not live." Yeah, he saw the essentiality of respiration. But the modern incarnation of pulmonology didn't begin until the 19th century. And with this guy, Osler. I had also kind of flashed by Osler, but here he is. And back in the 19th century, so 150, 160 years ago, it was really established by this guy and called physiology, PHTHISI. What a Scrabble word there. Physiology, and this was it all started with the attempt to address tuberculosis, which was a scourge at this time. So he started this Association for the Study and Prevention of Tuberculosis, which eventually, this was their symbol, eventually became the National Lung Foundation, which in more modern times has done a lot to work against smoking. So tuberculosis, although it feels like it's at bay, fully 1/3 of the planet probably has occult infection with tuberculosis. 1 out of every 3 humans on Earth probably has tuberculosis. So it's still a problem, right? and it's a sort of a bomb waiting to blow up. It's sort of held in check clinically by the administration of antibiotics that are not able to eradicate it often from these people, but are able to keep it at bay. But when antibiotic-resistant tuberculosis arises, that's going to be a major health issue in your people's careers. Yeah, in the next 50 years, you can look forward to that. It's going to be fun. So another bit of pathology is poliomyelitis. Poliomyelitis was a pathologic disease that basically killed off the neurons that were part of the phrenic nerve, for example, that assisted ventilation, and other neurons. It basically degraded myelin in peripheral neurons, and it hit the phrenic nerve. And so there were all these young children that were not able to breathe. And this is what the scene was not even 100 years ago, within the lifetime of your grandparents who may be alive. This would have been their generation. Children were stuck in these iron lungs. They are basically negative pressure ventilators. So they would go in there, this collar would go around their neck, like sort of an airtight collar, and then there'd be like a vacuum inside this iron lung that would forcibly expand their chest, and then they would have positive pressure, and it would expel the air. So the vacuum would pull the chest open, and air would get sucked into their mouth, and then positive pressure would push the air out. That was the birth of artificial ventilation. Obviously now we have much more sophisticated ways of doing that. But this picture up here was one of the very first of these things. And these young kids who were struck paralyzed and unable to breathe had to spend their lives like that, sitting there. That's not therapy. That's life. That's right where they were. So Jonas Salk received the Nobel Prize in Medicine for creating the vaccine for polio. And one of the scary things about this anti-vaccination movement out there, which I find to be irrational, is that diseases like polio are popping up in places around the world. Thankfully, here in the United States, it's been mostly eradicated, but measles and other problems that have not really been much of an issue for your generation, for young kids in places like California, it tends to be a liberal affliction, this anti-vax thing. It's rising up in some places, particularly in California on the West Coast. So, yeah, vaccines. All right, that's all my history for today. The alveoli. We're going to talk about really two things today. We're going to talk about ventilation, the process of ventilation, and then gas transport and how hemoglobin actually works. That's the take home today, is how hemoglobin functions. But first of all, these alveoli. I've talked about this surface area to volume thing numerous times, and it's hard to find an example as illustrative as the lungs, right? So the lungs folded up inside these two compartments in your chest. Yep, folded up in these compartments inside. Yes, no problem, absolutely. Are these lungs that the surface area of which is 35 times the surface area of your body. That's pretty incredible, right? So like inside my lungs is tissue that could roughly cover double the class in here. Yeah. So. All right, so these are the topics I'm going to cover. Go through. I'm not going to do the anatomy too much, but I'll flash through it. I'll talk about a little bit of pathology on the front end for you guys, some asthma and COPD. Talk about how ventilation works, pretty straightforward concept. Then some gas exchange, and then we'll get into the real fun stuff, hemoglobin. I probably won't talk a whole lot about carbon dioxide transport, and then I'm going to get on a soapbox about lung cancer. Okay. So here's that anatomy. We just talked about it all in the lab, but this is sort of the functional anatomy in that we have all of the anatomy of the upper respiratory system in the nasal cavity that assists in olfaction, all right? And I'll show just one cross-section of a frontal section of a head. So you can see how it really does increase the surface area so that the more surface area you have, the more odorant can get dissolved and come into contact with a sensory receptor, a nerve ending, and increase your sense of smell. Then phonation is the production of sound by the larynx. Phonation is different than articulation or enunciation. So for an example, phonation, if I were to sing Happy Birthday just phonating it and not articulating it, it would sound like this. I'm just generating the bass tone, the fundamental tones with my larynx, but I'm not shaping those tones at all with my oral apparatus, which is the articulation of sound, right? And then the epithelium, the mucosa on the inside of the trachea protects the respiratory system with the respiratory surfaces with this really charmingly entitled mucociliary escalator. And we'll see that little mucus escalator. We'll see what that means in a moment. Then, of course, there is gas exchange at the lung and ventilation, which is the movement of air to the exchange surfaces of the lung. The lung also is responsible. I don't know. I have to look ahead at my lecture for tomorrow. I sometimes have gone into much more detail, but the lungs also have purposes in. So, for example, they're responsible for converting angiotensin 1 to angiotensin 2. Like, it's related to like kidney function, and I think we'll see some of that tomorrow. Yeah, there are some endocrine functions in the lung. Oh, okay. So I just at the end of lab there decided to show a video because it's so fun. Why not? You guys ever seen a video of phonation? Check this out. It's in German.
Dies ist kein Röntgentonfilm, sondern eine Aufnahme mit der Magnetresonanztomographie oder kurz MRT, die auch als Kernspintomographie bekannt ist. Das in Göttingen neu entwickelte Verfahren der Echtzeit-MRT kann beliebige Bewegungsvorgänge im Körperinneren mit einer sehr hohen zeitlichen Auflösung aufnehmen. Da gleichzeitig auch der Ton aufgezeichnet wird, verdient die Wiedergabe der Sprache besonderes Interesse. Das Geräusch der MRT-Messung wird dafür weitestgehend unterdrückt. Dieser MRT-Tonfilm wurde mit 55 Bildern pro Sekunde gemessen. Man erkennt dabei Form- und Lageveränderungen des Zungenrückens, des Zungengrundes, des weichen Gaumens, des Kehldeckels und des Kehlkopfes. Achten Sie bitte auf diese Vorgänge bei den Vokalen A, E, I, O, U, sowie bei den Konsonanten L, M, N, R, S, T, V, W, B, P, H. Und bei den Zahlen 1, 2, 3,
So whatever.
4,
Internet's got everything.
5,
My
6,
TAs were like
7, 8,
showing me some.
Neun,
You can like watch open heart
10.
surgery. You want to learn how to do open heart surgery?
Vielen Dank
On
für
YouTube.
Ihre
I swear to God,
Aufmerksamkeit.
anything you want. Whew. Okay. Fun, fun, fun. Okay, so the point here, and you know what I sort of want to do, I've got a little picture of Jean-Luc Picard's face cut off here so you can see his nasal cavities. I should put a little picture down here of like a sea lion or something. It's pretty impressive when you compare. But you can see that these turbinates have a pretty significant increase in surface area right there. All right, moving on and down the line. The point, I don't know if I said it already, but the point of all that increase in surface area, the more surface area, the more nerve endings are going to be able to come into contact with odorants that you're inhaling and increase the your sort of the spectral density of your ability to smell something. All right, the mucus elevator. So that mucosa that lines the respiratory tract, that's all ciliated columnar epithelium. Those cilia and they're covered in a layer of mucus. They're all beating in a more or less coordinated manner to move the junk that's in your throat up. Like, so you inhale some dust, particles, whatever, lint, crap that's out in the air, and it adheres it gets stuck to the mucus, and these epithelial cells just brush it along up, and it slowly comes up. You expectorate it, maybe you swallow it, maybe you spit it out, who knows what happens to it, but it stays out of the lungs, which is good. We look closely at this, and we can see that there are these goblet cells, or mucus cell, which is going to release that mucus onto the surface of that columnar epithelium. All right, more beautiful pictures. Not a lot of other point to make about it, though. Okay, so here are the functions of the lungs. We've already hit gas exchange. And part of gas exchange, one of the consequences of gas exchange, is that the lungs are responsible for helping to regulate your acid-base balance. All right? By blowing off carbon dioxide, there's less carbon dioxide in your blood. Carbon dioxide that's dissolved in your blood can become carbonic acid. All right, and acidifies the blood. So the more carbon dioxide you blow off, the more you alkalize your blood. It helps to defend against pathogens. There are, did we talk about eosinophils? Yeah, we did. We talked about eosinophils in lab. Eosinophils are granular leukocytes that produce IgE. It's an antibody. It's really found high density in the lung tissue, and they're there to help us deal with any kind of inspired pathogens or aspirated pathogens, inhaled. It also acts as a blood reservoir. So the lungs have about 20% of your blood volume at any given time. That's a lot. That's a lot, right? So we said that it's 35 times the surface area of your body, and all of that surface area is deeply invested with capillaries. So there's like a huge capillary reserve of blood in the lungs. And then there's also this sort of endocrine functions. So this is where we make what are called leukotrienes. Leukotrienes are inflammatory cytokines for the immune system. We also activate angiotensin. We'll find out what angiotensin is tomorrow. And then there's the breakdown of epinephrine and serotonin. So circulating levels of epinephrine, aka adrenaline, the adrenaline that your body produces one way or the other gets broken down at the lungs, as does serotonin. So catabolism, have I defined catabolism for you guys yet? No? Okay. We'll talk about it. We're going to have a lecture about it on Thursday. But in general, catabolism is the metabolic breakdown of something, and anabolism, like an anabolic steroid, is something that drives the metabolic buildup of something. You're going to build something bigger, it's anabolism, and you're going to break something down, it's catabolism. So the catabolism, or the breakdown of epinephrine and serotonin, happens at the lung. Okay, this is a bunch of anatomy that we already saw, but I want to make these points right here with this. So that the medium level bronchi, the ones that you see right in here, are the primary site of resistance to air flow in the lungs. They have a bunch of smooth muscle around them and are able to either bronchodilate, that is to get bigger, or to bronchoconstrict, and that means to get smaller. Bronchodilation is driven by fight or flight, which makes sense, right? Like, werewolf senators from Mars come in and like, and I gotta run, need some oxygen, and then maybe I like switch places with you and have to sit in your seat and listen to me drone on. I'm just like, parasympathetic kicks in, and I breathe and gets shallower, and I nod off to sleep. Yeah. So, depending on a whole host of things like psychological context, are you inhaling or inspiring any sort of irritants of some sort, whatever, they're going to activate either sympathetic or parasympathetic nervous system and are going to change that resistance via bronchodilation or bronchoconstriction. So that's sort of an entryway to talk about bronchitis. Bronchitis is just an inflammation of the bronchial mucosa. And when we have it, it makes it harder to breathe. It makes it harder to move air into the lungs. The opening that we're breathing through is smaller, okay? Bronchitis can be caused by a bacterial or viral infection that you get because you've got a couple beautiful little kids that go to kindergarten and stick everything in the world in their mouths and then come home and like rub snot all over you because they love you. And you get something and you get bronchitis, right? Or you could be a person who has COPD, chronic occlusive pulmonary disease. And this COPD can also induce a type of bronchitis that doesn't resolve itself after you clear the infection that you have. This is serious. 10 million people in the United States have COPD. That's the population of New York City. And 40,000 people a year die from COPD alone. I'm not talking about lung cancer. I'm not talking about any kind of actual disease other than the fact that they cannot breathe. They suffocate. 40,000 people a year from COPD. yes, those people have COPD. The most common reason they have COPD is because they're smokers. There are other reasons that people get COPD. And then on the other hand, there's asthma. So asthma is got a different underlying molecular mechanism, but there are some similarities, right? So asthma is an atopic disease. It's called atopic, and for intensive. So an atopic disease is one type of an allergy. There are like 4 allergy types. Atopic disease is one of them. So asthma is a type of atopic disease. Other ones being hay fever, atopic rhinitis is another name for that. Atopic dermatitis or eczema is a third. Asthma. Some other atopic disease are itchy eyes. There are types of irritable bowel that are atopic. But in the lungs, it's called asthma. And so it's just a inflammation of bronchial mucosa. They have an infiltration of eosinophils. And so if you take a section of that tissue, you see what's called eosinophilia. It's like a high density of these granular leukocytes, really high IgE titers in their blood. These people get, one of the ways that we deal with this, I didn't get a chance to talk about the different types of receptors, alpha and beta adrenergic receptors. I cut those slides out. But you can use this stuff called albuterol, which is a beta-2 adrenergic bronchodilator. It basically hits the receptors that, like the sympathetic receptors that are going to like open up those airways, sort of inducing a fight or flight response just in the lungs. So that's, you've probably seen the like asthmatics with their inhalers. That's what that stuff is. And that's the molecule right there. All right. So I made the point already about 2 complete sets of vasculature in lecture. I'm going to skip on down the line past this. Is there any other point that I want to make to this? Should have probably deleted this slide. Okay. So I said the lungs have 20% of the blood in the body. I said the lungs have 35 times the surface area of the surface of your body, right? A lot of blood spread out over a vast surface area. Because of that, in these capillary beds, capillary blood is low pressure blood. Because of all of this, the pulmonary blood pressure is extremely low, all right? 30 millimeters per mercury. You guys measured your mean arterial pressure, didn't you? Yeah, you measured your mean arterial pressure. And all of you, I can tell you, all of you have low blood pressures, right? Totally healthy, not abnormally low, but very low blood pressures. All of those blood pressures were at least twice this number that I'm putting up here, right? So you can appreciate how low that pressure is. And because of that, we also talked about the fossa ovalis in the heart, right? We talked about the fossa ovalis in the heart and fetal blood circulation, which the fossa ovalis in utero was the foramen ovale. It was the compartment between the right and left atrium. Because the blood pressure is so low in the pulmonary circuit, the pulmonary system is really prone to having blood clots, little lumps of fat, air bubbles, whatever, get pushed through what's called a patent foramen ovale. So that foramen ovale doesn't completely close and at birth, and there's still a little bit of an opening. And because the blood pressure is a lot higher on one side of the heart compared to the other, this stuff gets pushed through that patent foramen ovale and into the pulmonary side, and we get what's called a pulmonary embolism. Pulmonary embolism is a good way to die. Actually, not a good way to die, but it happens quite a bit. So I believe the statistic is 1 in 5 people has some sort of patent foramen ovale. So the chances are that some person in this classroom actually has a PFO. Now, most PFOs go fully occult. They're fully occult your whole life. You never know that it's even there. All right. But some huge number of pulmonary embolisms, something like 75-80% of pulmonary embolisms, happen to people with PFOs. All right. So there's some numbers for you. Okay, so we looked at this anatomy. Were there any questions on any of that? We looked at this anatomy in the lab, and is there any other point that I want to make here? Well, the gas exchange happens in these respiratory bronchioles because it's the first place that we see the alveoli, and then it moves, the air moves down into the alveolar ducts and alveolar sacs. But the exchange happens at the alveoli, wherever they happen to be. So in the actual surface of the alveoli, we're going to find 2 types of lung cells. So pneumo, P-N-E-U-M-O, pneumo is the prefix that refers to the lungs. Pneumocyte is just a lung cell. There's 2 types, 1 and 2. Not very creative with that. But type 1 is just a simple squamous epithelial cell. That's everything that's in purple here. They're just a thin, actually incredibly thin, layer of squamous epithelium. And then these type 2 pneumocytes are called septal cells because they live in what's called the septum. The septum is just the wall between adjacent alveoli. These septal cells, they make a surfactant. Surfactants are molecules. They're basically amphipathic molecules. That is, molecules that have a hydrophilic and a hydrophobic portion to them. And there's these oily secretions that are made out of phospholipids and proteins in this surfactant. The goal of the surfactant is to reduce the surface tension. So what happens when you get some water on your skin, or you see water on the ground, on the counter? What does it do? It beads up, right? It beads up. And we need the surface of this epithelium to remain moist. But if the water beads up, what's the problem with that? Why don't we want water to bead up in the lungs? What do you think? Well, what's going on? What's the primary purpose of this layer? Yeah. Yeah, if you have a big bead of water, a big drop of water, the water's got to dissolve into the water, go through a huge drop of water, and then dissolve across this epithelium into these capillaries. You know, if you have a big bead of water here, this is a cell, right? A bead of water could like almost fill the entire alveoli, right? You don't want that to happen. You don't want that to happen. So you need a surfactant that reduces the surface tension of the water, keeps the surface moist, but spreads that water out. Okay? All right. So this respiratory membrane is essentially this alveolar epithelium. It's the squamous epithelium, the pneumocyte type 1. Then there's a little bit of basement membrane, and then there's the capillary endothelium. This distance is about 0.5 micrometers. That's 2/100,000ths of an inch. That is super teeny tiny, very, very thin, incredibly thin. Yeah. Well, why that? Why is it like that? Why is it that thin? It seems like that would be pretty delicate. Tear that pretty easily. Why so thin? What do you think, Emma? I'm putting you on the spot because I know you can do it. Why do we want this respiratory membrane so thin? Here's a red blood cell. Here's our blood. Here's the... Okay, Jason.
Do we want oxygen to be able to pass through it?
Super fast. Yeah. We want oxygen to be able to go through super fast. And we don't want it to have to go very far to do that. All right? So we breathe in. The way we breathe, we don't like... That's not how we breathe, right? We just breathe in, we breathe out. And we expect that oxygen to exchange as we do that. We don't want to wait for this long diffusion process. So that respiratory membrane is really thin. Okay. So here are the steps. There's pulmonary ventilation. That is, the diaphragm does its thing, and gas moves in and gas moves out. Once it moves in, it's going to diffuse across that membrane, and then we're going to transport it to the peripheral tissues. Once it gets to the peripheral tissues, there's going to be internal respiration. And internal respiration is a totally different discussion. In fact, we're going to talk about internal respiration on Thursday when we talk about how we use food, right? So we're going to get to internal respiration later. Today we're going to talk about external respiration, and in fact, we're going to talk a little bit about these two, the pulmonary ventilation and gas diffusion, and then I'm going to spend a lot of time, hopefully about an hour, talking about transport. Just a couple definitions for us so that you know these words. Hypoxia is just hypoxia, low oxygen levels. Anoxia, and meaning no oxygen, no oxygen. So it's anoxic tissue is completely devoid of oxygen. And then apnea is a temporary cessation of breathing, particularly during sleep. Yeah, apnea can be a real problem. I was just actually reading an article about former NFL retirees, linebackers. So everybody talks about concussions in the NFL, but linebackers in the NFL are encouraged to put all this weight on when they are working, and they get huge. But then when they stop, when they retire after 10 years or something, they have a really hard time losing that weight, and a lot of the muscle turns to fat tissue on their bodies, and they have like joint problems because they're overweight anyways, and they've been beat up on the field, and so they don't exercise, and all of this extra weight that they're having exacerbates apnea. So sleep apnea is highly correlated with obesity, and the lack of so that sleep apnea leads to really poor sleep quality, which raises cortisone levels and leads to diabetes and heart disease and other issues. So apnea is a real health concern. Learning how to deal with sleep apnea is not just about getting a good night's sleep. It's about total health for the individual. So there's a real move towards getting people to wear what's called a BiPAP, which is like a positive flow air mask at night and help prevent apnea. Different types of apnea, but that's enough on it. Okay, so Boyle's law. Holy cow! High school physics. Oh no, no. Real easy. Pressure is inversely correlated with volume. Very simple. How are we going to memorize that? Who has seen Star Wars? I remember, like Jenny said she hadn't. Is anybody else not familiar with Star Wars? Okay. Well, anyways, when the volume goes down, so here's Luke and Leia and Han Solo in the trash compactor, and the volume's going down. As the volume goes down, the pressure's going up on them to get out of there. Whereas here's Luke out here on Tatooine, like calmly watching two sunsets in the vastness of the desert. Low pressure, large volume, high pressure, small volume. That's all there is to ventilation. What does this even mean? Well, when you are inspiring or inhaling, you are creating a larger volume in the lungs and reducing the pressure there. And by reducing the pressure's larger atmospherically, and it pushes air into the lungs. And then when you're exhaling or expiring, you are going to increase the pressure by decreasing the volume. You're compressing the lungs. That increases the pressure and just forces the air out. Pretty straightforward. Here's the yogi in me, there is, of course, the thoracic diaphragm, but there's also a pelvic diaphragm that does play a role in ventilation if you're really breathing with your whole torso. Okay, so that's ventilation. Now let's look at gas exchange. So we've gotten the gas down to this exchange surface, and let's look at what happens. So the pressure, the partial pressure of oxygen, so that when I say pressure, that's another way to think of it as concentration, dissolved concentration, okay? We'll call it pressure because that way we can compare it to the pressure in a gas out here in the outside world. Think of it as a concentration. The partial pressure of oxygen in your venous blood, deoxy blood, is about 40 millimeters of mercury, about 40 torr. Whereas the partial pressure of carbon dioxide is about 45. It gets down here, and it turns out that the air we're swimming around in is about 100 millimeters of mercury oxygen and about 40 millimeters of mercury carbon dioxide. So there's a really strong gradient for oxygen to travel down here. Oxygen is just going to dissolve into your blood very rapidly, and carbon dioxide is not going to be as urgent, but it will go down its gradient and diffuse in that direction across the membrane. Okay? And then this blood now arrives, that has been fully oxygenated and had its CO2 depleted, arrives at the peripheral tissues. And at those peripheral tissues, the partial pressure of oxygen is about 40 and carbon dioxide is about 45. So we get exchange in the opposite directions down their gradients. Fairly straightforward. Okay? Any questions on this? So I'm about to dive into hemoglobin and how the transport actually works. Any questions back here before I get going? No? Okay. Hemoglobin. So we looked at the structure of hemoglobin a little bit already. It is a quaternary structure protein. It has 4 subunits, 2 alpha and 2 beta chains. In each of these globulin chains, there's this little thing that is stuck in there called the heme. Heme is So if you were to take iron out of that, this thing would be called a porphyrin ring. So heme is a porphyrin ring with iron inside. It's basically like a little trampoline. You can imagine this as like sort of a molecular trampoline. It's all stretched out. It's got iron kind of like sitting in the middle of it. What do we know about iron? Well, depending upon the oxidation state of iron, it likes to bind oxygen. It likes to bind oxygen, right? I mean, here is a model of hemoglobin, and here's that same model after it has been oxidized. All right, it's rusted. So these red blood cells are packed with this. Packed. Each red blood cell has 280 million, just one red blood cell, 280 million hemoglobin molecules. There are literally billions of these buggers in you. Okay, so let's look at it a little bit more closely. I said Fe2 plus likes to bind oxygen. Yep. The binding of oxygen can shift the oxidation state of iron. So we can have either iron, Fe2 plus, bound to oxygen, or it can form what's called the superoxide ion. When that happens, the formation of the superoxide ion is going to cause a conformational shift in this thing. So here is the histidine. It's one of the amino acids in the globulin, which coordinates with the iron, and here's the porphyrin ring that's embedded in this. When it binds oxygen, the weight of the oxygen that is attached to this shifts the molecular structure super slightly, right? I mean, there's a little bit more, not inertia. There's more mass. It's a mass effect, really, that pulls this iron this way, shifts all this geometry and the geometry down along that histidine by only 0.4 angstroms. Doesn't seem like much, huh? But it has profound implications. Specifically, it has implications in how the porphyrin rings, the heme, the iron, in the other three subunits in hemoglobin, their affinity for oxygen is going to be affected by this. All right, I'm introducing a concept called allosteria. We'll get to that in just a moment, but this is the idea that when a molecule binds its ligand, or the thing that it's supposed to bind, it's going to affect how readily that protein is going to bind more of them down the line. Okay, allosteria. So for example, here's deoxyhemoglobin. No oxygen bound at all. And these two subunits are rotated 15 degrees with respect to one another. One of the things you'll notice is this molecule looks a little bit like a donut. There's like a space right in the middle here. Whereas when we oxygenate it, it kind of dials in on itself a little bit, without bonking myself, dials in a little bit, closes the space off, and affects the ability with which any unoxygenated hemoglobin or heme molecule is going to be able to bind oxygen. Okay, so here are some GIFs. All right, you can kind of see. So these are based on X-ray crystallographic structures that have been overlaid. So where is it? Yeah. Here's the oxygen bound and then unbound. So bound, you can see it pulls that histidine this way, which causes a conformational shift in the whole molecule. You can see it happening here again. So as oxygen binds, it causes a really slight conformational shift. This is called allosteria, the alteration of the activity of a protein through the binding of some sort of effector molecule at a site. So an effector molecule is just a molecule that's causing an effect in the protein. This means that the individual subunits of hemoglobin have what's called cooperativity. They cooperate with one another. That when it binds oxygen in one of the 4 sites in a hemoglobin molecule, it transmits that information through subtle molecular shifts or conformational shifts to other sites and affects the function of those other sites, how readily they're going to be able to bind oxygen or not. You guys with me so far? Who's lost yet? No? Good. Yes? No? This slide here is I'm going to spend at least 5 minutes on this slide because if you can understand any slide in this lecture, it's this one. So what I'm looking at here is partial pressure of oxygen along this axis and percent saturation, all right, across an ensemble of hemoglobin. So I'm going to have a teaspoon of blood, or a cc, a cubic centimeter, a milliliter of blood. And within that, there's how many millions of red blood cells. And this is the percent sites that are saturated of hemoglobin. Like this is the percent of the carrying capacity in that hemoglobin. So at 0 partial pressure oxygen, obviously there's going to be no saturation, right? There's no oxygen to saturate anything. And at 100% saturation, that happens at coincidentally at about 100 torr. This is not a percent. It just happens to be that that's the pressure at which you get 100% saturation. Also happens to be that that's the pressure of oxygen in the atmosphere, all right? Which is why this evolved to be that number. And in between, you might think, well, would it just be a straight line going from here to here? No, this is, yes, it would if it was not allosteric or there wasn't a cooperativity between the sites in the hemoglobin. But it is allosteric. And so there's this shape to the curve. And we're going to walk through why it's like this right now. So these are the 2 pressures of oxygen in your veins. Your vein has about 40 millimeters of mercury or 40 torr of oxygen. And your arteries are about 95 or 100, right? So this is oxygenated blood and this is deoxygenated blood. So normally, the blood is just going back and forth, and delivering oxygen. This is your systemic tissues at rest, when you're just sitting there. No politician werewolves are after you, nothing. You're chilling out. And this is the same when after you've taken in a breath in your arterial blood. So what is going on? There's a few things that are a little bit, that might be strange to you at first when you look at this. Does anything pop out? What do you think? What percent saturation do we have in our venous blood? 75. 75% of the sites that carry oxygen are full of blood, are full of oxygen, right? When we are at our most deoxygenated. Does that seem efficient? Obviously, no. Why is it like that? What do you think? Speculate. Somebody. Lindsay, you have an incisive mind. Give me a thought. None? What about Trisha? You guys are like right in front of me. I'm just asking you because you're right there. Have any thoughts? I'm just going to keep moving in this forward line. Trinity, how about you? What are we doing with all this here, right? Think about this like the bank. Okay, Miles, you want to answer. Let's hear.
I'm thinking maybe if you stop breathing or if your heart stops beating, you have a reserve of oxygen so that you don't die.
Right there. Exactly. It doesn't have to be anything that radical either, right? It doesn't have to be that radical. It just has to be like Mitch McConnell as a werewolf. Like coming in and like I'm running and I need to use oxygen quickly. Right? And so I can dip into this reserve. And the thing is now, look at the way this curve is shaped. Up here from this point to this point, the slope is more or less like that, isn't it? But from this point to even just right here, the slope is like that. So once you get past this point here where you're dipping below what is typically the normal concentration of carbon dioxide or oxygen in the blood, if we're using this up, we go down here, say we're like, the cells are starting to pull oxygen in rapidly, burn oxygen rapidly, moving into aerobic territory. We want these red blood cells to offload that oxygen very quickly, don't we? So for a shift for a smaller shift in partial pressure of oxygen, we're going to get a much bigger change in percent saturation here than we are going to be over here where it's business as usual. Does that make sense? It's like we got 3/4 of the oxygen in the bank for when we need it. I feel like I could go through this a little bit more still, but we'll just keep going and see how it goes. So here's an example of that. Here we are at 40 at rest, and here we are. So this is 40 in the veins. This is 100 in the lungs, in the arteries, and going back and forth, we're delivering about 21% of the oxygen that the hemoglobin is capable of delivering. And now if we exercise, when you're exercising, maybe you shift that partial pressure of oxygen at the peripheral tissues down to 20 torr. Not that much, right? Because we're going here from, this is a 60 shift, and we're only delivering 60 torr shift, and we're only delivering 21% of our oxygen. Whereas when we move it only 20 millimeters of mercury, or torr, we're going to deliver an additional 45 because of this shape, right? Because the binding of one hemoglobin affects the affinity that another has. So if you start to exercise, you can deliver up to 2/3 of the oxygen that the cells are capable of delivering. What else do I want to say here? Okay, so here are a couple models for how this works. There's this sequential mode model of cooperativity and a concerted model of cooperativity. The idea that I want to introduce, whatever model you use to think about how it works, is that there is a T state and an R state. A T state and an R state. And that's how we're going to try to understand this, and how the binding of oxygen shifts us from the T state to the R state. So the T just stands for tense. And the R just stands for relaxed. And the T state has a lower affinity for oxygen. Just imagine being tense, and it's like, it's harder to breathe when then you're relaxed. Binds oxygen better. All right. So let's look at this. Down here in the veins, when you are low concentration of oxygen, this T state is going to be favored. The T state is going to be favored. This is so that hemoglobin is going to have less of an affinity for oxygen, and whatever oxygen is still on the molecule, it's going to offload it, right? So when hemoglobin is in the peripheral tissue, it's not going to want to hold on to its oxygen. It's going to be likely to be in the T state and have a lower affinity for oxygen. Does that make sense? If it's confusing, raise your hand. A little bit, yeah. So if we were going to design a hemoglobin molecule, we would want to design one that as it's transporting oxygen, whatever oxygen it held, if it was in a low oxygen environment, we would want it to have a lower affinity for oxygen, so it let go of the oxygen, so it can deliver its oxygen to the tissues. And at a higher concentration of oxygen, like the lungs, we'd want it to be in a state where it had a higher affinity for oxygen. So it would bind oxygen more, right? So when we're at high partial pressure of oxygen and oxygen's binding, it shifts towards the R state so that it's like it is more avid for oxygen. The hemoglobin will bind oxygen more strongly, more readily, and doesn't want to let it go. Hemoglobin in high oxygen binds tightly to oxygen. Hemoglobin in low oxygen concentration binds poorly and releases the oxygen. This is why that curve looks, or I guess for you guys, the curve looks like that sigmoidal shape. So they say, there's this concerted thing where all of the sites change together, or there's this sequential model where one changes and it like slowly with time affects the state of the other things. They don't really have a good idea, or maybe they do. This slide's a couple years old. All right, T state and R state. Let's think about it more. So if the world was only made of T state, like hemoglobin couldn't shift, there wasn't this conformational shift that happens when it binds, the binding curve would be pretty much like this straight line right here. This is the T state binding curve. This is what our saturation dynamics would look like. And on the other hand, if it was only an R state world, it would be this blue line. So what we actually see is something in between them. Okay, the curve that actually exists is something in between the T state and the R state, in the ensemble of blood. That's the actual saturation dynamics. If you add a partial pressure of oxygen, you measure what the saturation is in the hemoglobin, you get the purple curve. But it's more complicated than that even. Oh, no. Hemoglobin is amazingly complex. I'll say that. We're just going to scratch the teeny tiny surface of this. In graduate school, there was an upper level graduate class at Notre Dame, enzyme kinetics, that basically talked about hemoglobin the whole time, nothing but hemoglobin. A whole lecture, not just a lecture, a whole class. Drive you insane. We're going to get a little bit of it, though, because it's pretty beautiful. It's pretty incredible. All right. Enter 2,3-bisphosphoglycerate. 2,3-bisphosphoglycerate. Does everybody, before I move on, does everybody understand the basics? Did you get R state, T state? Anyone else? Need me to belabor it a little bit? No? Yes? Shake your head. Yes? No? Okay. Pure hemoglobin. Yeah, right. So 2,3-bisphosphoglycerate. 2,3-bisphosphoglycerate is a metabolic intermediate. All right. So when you talk about like how your body burns sugar, right? We've talked about how it breaks down glucose. Glucose is the 6-carbon sugar. We break it in half, and we're going to make 2 pyruvates and then send the pyruvates down through the Krebs cycle and the mitochondria and all that, make it ATP. 2,3-bisphosphoglycerate is up in the like glycolysis portion as we're heading towards pyruvate. It is like a side path. It's like in a side path that the cell can go down. All right, a molecular detour that'll get us to the same place. But the point is that it's a metabolic indicator. It's a metabolite that's sort of a metabolic indicator of what's going on in the cell. Are you burning a bunch of sugar? Meaning, do you need a bunch of oxygen or not? Well, it turns out that 2,3-bisphosphoglycerate is going to affect the saturation dynamics of hemoglobin. So without 2,3-bisphosphoglycerate, BPG, the saturation curve of hemoglobin looks pretty close to the R state. It doesn't actually look like it's somewhere in the middle. It looks pretty close to the R state. Whereas when you have it, this is what gives us the R or the T state mix. All right? It helps, the point is, it helps to stabilize the T state. It helps to stabilize the T state. Okay? So let's think about why that is. I just said 2,3-BPG is a metabolite. Where are we going to find it? Is this stuff going to be hanging out at the lungs? Is it going to be in the peripheral tissues? Is it going to be found more in high oxygen blood or low oxygen blood? Yeah, it's going to be found in low oxygen blood, near the peripheral tissues. All right? And so we know that peripheral tissues are at about 40 torr of blood, right? Or let's do it at 20. This chart has this, it's showing this line at 20. So we're exercising. And that's when you would produce a lot of BPG, 2,3-BPG. It's when you're actually running and burning sugar is when you'd actually find 2,3-BPG. So at 20 torr with BPG, you can deliver 66% of the oxygen that's being carried by hemoglobin. Without it, this is the curve, you're only delivering about 8% of the oxygen because the oxygen has a much higher affinity. We're in the R state. The hemoglobin likes to bind oxygen much more. It's up here around 80%. Or 90%, whatever that is, whatever the number is. Does that make sense? Following me? Okay. So, here's the actual pathway. What do you know? How fun. Molecular models, oh my God. Well, there's glucose. If you've never seen it, that's what it looks like. That's sort of the bread of life. For real. And we break it down through glycolysis. And as you go through the glycolytic pathway, one of the things you get to is 1,3-BPG. And then we can take that right over here to 3-phosphoglycerate, which then becomes pyruvate. But there's this side pathway where we can go right here. When we have low pH, that means high hydrogen ion concentration, it's going to facilitate this enzyme, this bisphosphoglycerate mutase. Low pH, high hydrogen ion concentration turns on this protein, and it stops this protein, the 2,3-bisphosphoglycerate phosphatase. Long name. But the point is, at low pH, we start building up this stuff. Low pH is what happens when you go high carbon dioxide concentration, high lactic acid concentration, high metabolic activity, burning a bunch of sugar off, all right? So as you're like running and your muscle cells are doing whatever they're doing, it's acidifying your peripheral tissues. pH is going down, carbon dioxide is going up, right? And that makes this stuff build up. This builds up, and it's going to give us this saturation curve rather than that one there. It's going to, all that extra 2,3-BPG stabilizes the T state. Okay, hemoglobin, like I said. Okay. So let's look at what this means. And this is getting at what I'm doing is heading towards babies. If you haven't noticed in this class, like everything I do, like has some sort of roundabout thing to get to babies because babies are so sweet. All right, what are you talking about, babies, Dr. K? Here it is. Let's do this. Remember the donut that I talked about? Well, what do you know? What's right? What fits in there? Right in there, 2,3-BPG. It's like the, what are they called? Like the, what are the donut holes? It's the what do they think? Munchkins. 2,3-BPG is like the munchkin in the donut here. It fits right in there. It fits right in there, and if it fits in there, this protein can't do that 15-degree rotation towards the R state. It's stuck in the T state. It gets stuck in the T state. The little munchkin is in there and gums up the works. How does it fit in there? Well, it is coordinated by these 2 histidines, these 4 histidines, these 2 lysines that are all right around there and coordinate with the phosphate groups on the 2,3-BPG. Stabilizes the hemoglobin. Okay, well, what happens in babies? In babies have, and not just babies, fetuses. When I'm saying baby, I mean in utero. Fetuses, they don't have the same hemoglobin that you and I have standing here. They have fetal hemoglobin. And fetal hemoglobin has this histidine mutated to serine. It's changed to serine. Okay? Because of that, 2,3-BPG does not like to be in that hemoglobin as much. All right? It doesn't have as high of affinity for fetal hemoglobin. Because of that, the fetal saturation dynamic is closer to that R state that I showed you earlier. And let's see what implications that has. So here, for example, at whatever concentration at peripheral blood we're at the placenta, right? At the placenta, we're on the mother's curve right here, where she's got about, 25% saturation. But at this same concentration of oxygen, the baby wants to be at about 50 or 60% saturation. So that's going to mean that the baby's hemoglobin, because it doesn't have as much BPG in it, it's going to have a higher affinity for oxygen. It's going to be more in the relaxed state than the tense state, and it's going to, as a consequence, at that placenta, drag oxygen off of the mother's hemoglobin onto its own. All right? It's going to pull oxygen off the mother's hemoglobin and stick it onto the fetal hemoglobin. Fetal hemoglobin has a higher affinity for oxygen than maternal hemoglobin. All right? It's an important concept. An important concept. And so the way fetal hemoglobin works, adult it has 2 alpha and 2 beta. Fetal has 2 alpha and 2 gamma. It's the gamma hemoglobin, the gamma subunits that are different in fetal hemoglobin. Yeah? Okay. Oh, look, baby. So when a baby takes that first breath, this is why doctors traditionally used to like smack the baby on its ass to get it to go rah! Like scream. That first big breath inflates the lungs, increases the blood pressure on that side, the pulmonary circuit, and shuts off the foramen ovale. It will eventually become the fossa ovalis. It also shuts off the ductus arteriosus. I'm not that tall, but you see it right up there. Okay? That center thing is the ductus arteriosus that closes off because the pulmonary pressure inflates, and that becomes a thing, and it helps to shut off that part of that vasculature. Okay, so I could probably have done without this slide, but this is just showing that it's not just the gamma. Gamma happens. There's also this I don't even know. Eta? Is that eta? Is that the Greek letter? Is that epsilon? Yeah. Okay. There's epsilon chains. Thank you. That start early on, prior to 6 months, drops out, and then the alpha 2, gamma 2 comes in. And then right here, this is where I'm heading. Right here, this is birth. All right? At birth, that moment, really, it's a super magical moment when a baby comes into the light. Right? It takes its first breath. Its whole circulatory system switches over, like all the plumbing changes, and it causes this radical shift in the production of hemoglobin. Fetal hemoglobin gets recycled, and adult hemoglobin, they're not an adult yet, but the alpha 2 beta 2 hemoglobin starts getting produced. All right, because they're not on the umbilical cord anymore. They're not getting blood through the placenta any longer. So this is like a pretty complex looking slide, but I'm not going to ask you to like memorize all of it. The reason I'm showing you this slide is because I want you to see how hemoglobin gets recycled a little bit, so I can talk about why some babies are jaundiced. Is anybody like a much older brother or sister to some of their little babies? Has anyone like ever been around a newborn? Anyone? Some of you been around a newborn? Has anyone ever seen a yellow baby, a jaundiced baby? Okay. Well, we'll get to it. So red blood cells, they get eaten by some phagocytic cells. And this releases the heme, right? The heme is the porphyrin ring with the iron in it. Well, heme can get broken down in a couple different ways. One of the ways is it gets converted into something called biliverdin, which then can become bilirubin, Bilirubin and biliverdin are your bile salts. They are what make up bile. They are green and red. Biliverdin is green. Bilirubin is red. And they're the reason red and green together make brown. It's the reason your poop is brown. Bilirubin gets taken up by the liver and gets put into your feces, right, through the bilirubin, these other stercobilin, etc. But it's this bilirubin, this red pigment that's in the blood, that's what I want to talk about. So at birth, the baby starts turning over massive amounts of this hemoglobin, all right? Starts turning over massive amounts of hemoglobin and liberating a lot of this bilirubin that's getting shunted over to the liver and to put into the gut. This is why a large percentage of babies, healthy babies, totally healthy, this is not pathologic, they have newborn jaundice because they have a high level of bilirubin in their blood from the hemoglobin that got broken down from the fetal hemoglobin, because they don't need the fetal hemoglobin. They need adult hemoglobin. So there's this rapid turnover that happens right at birth, and it gives us these jaundiced babies. They turn in kind of yellow. All right. Luckily, it's easily treated with UV phototherapy or just mild exposure to the sun. Just go sit in the sunlight with your baby. I remember doing this with my daughter in Texas. She was born. She was kind of yellow, and we just got to sit with my newborn baby in the sunlight on the porch. It was such a beautiful thing. Okay. Any questions about that stuff? So I'm going to talk a little bit more about hemoglobin, just a little bit more. Believe me when I tell you, hemoglobin is a wild frontier, man. The dynamics of hemoglobin, there's fairly sophisticated stuff. But we're just going to talk about a couple other aspects of it. The Bohr effect and the temperature effect. So this guy, Christian Bohr, who was Niels Bohr's cousin, Niels Bohr, the famous physicist that came up with a model of the atom. This was his cousin, Christian Bohr, who was a physiologist who in 1904 established that the saturation curve in hemoglobin is affected by pH. It's affected by a lot of things, all right? There's actually a ton of stuff that's going to affect this saturation curve and make it more like the S or more like the T or more like the R, okay? And pH is one of them. As pH goes up, meaning more alkaline, less carbon dioxide, it switches towards the R state. As pH goes down, meaning more acidic, meaning higher concentration of carbon dioxide, it goes towards the T state, all right? And that should make sense, right? T state means likes to unload oxygen, right? Lower affinity for oxygen. Hemoglobin's unloading oxygen. If it's in an acidic environment, it's more likely to be at the peripheral tissues, isn't it? Or it's more likely that you're running and in acidosis because you are exercising vigorously. And so that is going to shift the whole curve to a point where at any given partial pressure of oxygen, so say we're right here, we're exercising, at the blue line, at the lower pH, I'm going to unload more oxygen than I would at a higher pH. All right? Does that make sense? The same happens with temperature. So there's a strong effect of temperature. as temperature goes up, you unload more oxygen. You go closer to the T state. That should make sense too, right? Because as you exercise, your body temperature goes up. And so at any given temperature, you're going to, so right here for, say, this partial pressure of oxygen, maybe we're right here, at a higher temperature, I'm unloading more oxygen than I would at a lower temperature. Yeah? Whose head is swimming? Callie? No. Mine's kind of swimming. It's like intense stuff. Okay. Oxygen release. Yeah. So that's everything I already said down there. Let's look at this. Let's just dissect it one last time so we can see if we can understand it. So this is the effect of carbon dioxide on the effects of pH and carbon dioxide. So it's like pH and carbon dioxide are going to run together, right? Because carbon dioxide is one of the ways that the body regulates pH, right? So the amount of carbon dioxide in the blood translates to carbonic acid, which translates to lower pH. So those two are tightly correlated. Let's look at the curve in red. So this is at a fairly alkaline pH with no carbon dioxide. In this scenario, we are delivering about 66% of the blood at this, tissue line that we've drawn right here. This tissue line, we're delivering about 66% of the blood. But if we acidify it, we make it pH 7.2, still with no carbon dioxide, we're getting rid of 77% of the blood. If we keep it at that pH, but now add carbon dioxide to it, we're getting rid of 88% of the blood. So carbon dioxide is also an effector. It also stabilizes the T state. Carbon dioxide stabilizes the T state. All right. So pH, temperature, and carbon dioxide all affect what state the hemoglobin finds itself in. And then there's carbon monoxide. Carbon monoxide. So the thing about carbon monoxide is it has a binding constant that's 200 times stronger than oxygen, okay, for hemoglobin. Carbon monoxide, once it binds, it is 200 times more likely to stay on there moment to moment than an oxygen molecule is. So if you have a chronic exposure to carbon monoxide, you slowly poison off all of the hemoglobin. You take them out of commission where they're not able to pick up oxygen and deliver it. All right? Slowly, the carbon monoxide competitively inhibits the hemoglobin. It binds and displaces the oxygen from the hemoglobin. So when I was the first teaching gig that I had, where like anatomy and physiology teaching gig when I was out of school, was at this place called Del Mar College. It was like a nursing school in Corpus Christi, Texas. And I would walk into that class and before these tests, right? And you guys are all such badasses here. I'm always impressed by Colby students, and maybe part of that. I'm not dissing Del Mar, but it was definitely a different culture down there. And you would go into these classes, and as you're walking in the building, there would be like half the class huddled outside of the test, just like sucking down a cigarette as hard as they possibly could, as if like the answers were somehow in that cigarette. They're just like getting it into their brain. Always was flabbergasting to me because they were like doing the worst possible thing they could do for themselves before the exam. They were just loading up their hemoglobin with a bunch of carbon monoxide and preventing their brains from actually being able to function properly. Yeah, this is what classrooms used to look like. Thank God we're not there any longer. But where people were just puffing away at the board, holding forth. We're so much smarter now. Okay, carbon monoxide poisoning. All right, so here, this is a slide that's sort of summarizing all these effects that I've talked about. Hemoglobin. Yeah, man. So we know that this is closer to the R state, and this is closer to the T state, right? R comes before T in the alphabet, right? So the R state is over here, T state is over here. And these are the factors that drive us in either direction. So decreasing temperature drives us towards the R state. Decreasing CO2, so decreasing concentration of carbon dioxide, drives us to the R state. Decreasing concentration of 2,3 diphosphoglycerate drives us in that direction. Also, increasing pH will drive us in that direction. These are all, if you think about this, these are all things correlated with rest, sort of, right? Whereas things going in this direction, increasing temperature, increasing concentration of carbon dioxide, increasing concentration of 2,3-bisphosphoglycerate, and decreasing pH. Those are all things associated with exercise. They're going to like drive us towards the T state and enable us to deliver more oxygen more readily at the tissues. Yeah.
What does the partial pressure 50 mean?
Okay. So that just means the partial pressure at which 50% of the sites of hemoglobin are saturated. Okay, that's all that means. And it just means there's going to be an increased. So it's the pressure at which you're going to reach half saturation. All right. So it's you're shifting it this way. So it's at a decreased pressure. So you're going to a lower pressure at which you're going to get to 50. Whereas an increased partial pressure, I didn't make this image, I'm sorry. It just has that on there. I didn't talk about that. But it's just like the pressure at which you get to 50% saturation. Okay. Okay, so that's hemoglobin. Does everybody feel mildly apprehensive about that? Is everybody good? Okay. Yeah, it's amazing. Hemoglobin, that's really, I'm not to frighten you, but that's really just the tip of the iceberg with hemoglobin. It goes pretty deep. So here is a summary. The top panel is how we move oxygen around. So oxygen comes in, jumps onto some hemoglobin, the red blood cells go to the tissue, and then the oxygen jumps off, always moving down its concentration gradient. Likewise, carbon dioxide is going to come back following its concentration gradient, but the mechanisms by which it moves are a little bit more nuanced. So some carbon dioxide is just going to dissolve right into the blood. It's just going to dissolve right into the blood. Some of it is going to enter the red blood cells and be picked up by hemoglobin. Hemoglobin will pick up carbon dioxide. I told you that carbon dioxide is an effector of hemoglobin, right? It will bind to hemoglobin. So hemoglobin can transport carbon dioxide. But carbon dioxide can also form carbonic acid and bicarbonate. And so this bicarbonate goes through what's called a chloride shift. And it gets pumped out of the red blood cell, and chloride, to maintain ionic neutrality, chloride goes in via this antiporter. We call this a chloride shift. This carbonate in here acts as a buffer in the blood to the carbon dioxide, which will become carbonic acid itself. All right? So there's like a buffering effect that happens here. These are two elements of a buffer for those of you who remember what buffers are from general chemistry. And then this is going to produce that H+, which is also going to be picked up by the hemoglobin. So we get over to the lungs, and we just do all that in reverse. Hemoglobin releases carbon dioxide. That goes out. We pull the carbonate back into the red blood cell and kind of reverse that chloride shift. And that combines with the hydrogen ion that was being carried by the hemoglobin. And we reconstitute carbon dioxide to be able to be exported. The take home there is that there's a number of mechanisms that are used to transport carbon dioxide, which lead to the buffering in the blood or the stabilization of your pH in your blood. We want to have a very stable pH in the blood, and it's related to how carbon dioxide is transported and exhaled and blown off. All right, so that's all the actual science we're going to talk about today. And then it's just smoking. I mean, not going to embarrass anybody and ask anybody in the room if they smoke, but I hope you don't, only because I care about you. So in this little panel up on the left-hand side, hopefully we're all on the blue line there, never having smoked, your respiratory performance, right? So this is just the percent ability to ventilate as per when you were 25 years old. So you guys aren't even on this chart yet. No one here is 25 yet. But as time goes on, everybody's ventilatory capacity goes down. Except a regular smoker, it's a much more precipitous drop. Until a smoker decides to quit, and then you actually arrest the precipitousness of that decline, and then you run parallel to what you would have been, but you never make up that deficit that you sustained by being a smoker. So you can reduce your risks of lung cancer and COPD and pulmonary deficit by stopping smoking, but you can never sort of recover what you had lost by doing that. And what is this? Okay, so 100% of the cases, right? So 90% of lung cancer comes from cigarettes. If you have lung cancer, 9 in 10 people got it from smoking cigarettes. And that's not the only way to get it. You can get it from occupational carcinogen exposure. That means like mesothelioma, which comes from exposure to asbestos, or blah, blah, blah. There's a lot of different ways. But there's a fair number of people that can get lung cancer from radon here in Maine, because the geology of Maine is such that the granite, the bedrock, has a lot of radon in it. Radon is a noble gas, a radioactive noble gas that is often in a lot of people's basements. And if you can get your basement tested for radon. If you do have it, then they have to put in radon mitigation stuff, like they blow it out. Has anybody ever had a house that had radon issues in it? It'll give you lung cancer if you don't make sure to ventilate properly. Yeah. So, sir.
I don't smoke anything, but
Yep.
I'm just wondering, if you get the same infection like smoking like marijuana or like electronic cigarettes and stuff like that.
Mm-hmm. Yeah, electronic cigarettes, I actually can't answer that question. I don't know if anybody knows because there hasn't been, electronic cigarettes haven't been around long term to be able to see what the long-term effects are and what the tar deposit is. But I imagine you could analyze the stuff and predict. I can't believe they're good for you. I don't know. I'm not going to make a statement about those. But marijuana, you have to be a pretty committed pothead to smoke as much marijuana as most people smoke cigarettes who are cigarette users. That being said, yeah, marijuana has tar in the smoke, right? So I don't know. I'm guessing that you've seen pictures of what a bong looks like that's been used chronically, right? And so, like, if it's in the bong, it's going to be in the person's lungs, right? And if it's in the lungs, it's yeah. Yes, the short answer is yes. The extremity, I don't know how to actually compare because there must be. I'm sure there's literature about that. Anyways, this is everybody in the classroom's lungs, and this is your lungs if you smoke. I don't know. Scare tactics. I'm not sure. I've seen this though when I was in medical school. The one of the cadavers we had to dissect was a smoker, and man, what they do to those lungs. So what do we have here? Yeah, some numbers, math, economics. The NIH estimates lung cancer care costs in the U.S. in 2015, so this is 4 years old now, was $13.4 billion. That's 2.5 walls. Yeah, so lost productivity due to early death from lung cancer was an additional $36 billion. $36 billion. It's a lot of money, folks. Just to put that into your personal perspective, everyone's personal perspective, that's $150 per person per year. Every man, woman, and itty-bitty baby child in America, $150 of their contribution to the GDP goes towards dealing with cancer and lost productivity thereof. That's a lot of money, man. So American Cancer Society estimates of lung cancer in the United States for 2017 are about 250,000 new cases of lung cancer per year, and a few more in men than in women, and over 155,000 deaths from lung cancer, more in men than in women. So here's that chart showing what's been happening. Early on in the 80s, they had recognized that cigarettes were hazardous, of course, and so they started putting warnings on, and men started quitting smoking, and fewer started smoking to begin with. But those tobacco companies, man, they're clever, and they sort of took the women's liberation movement of the 70s, where there was this idea of equality for women, and gave them an equal chance to get lung cancer. So they started marketing aggressively towards women as being a part of the American demographic that was more. It was an expansion market. It was a way to make money, killing off more people. Not just women, particularly African Americans. There's a lot of reasons that a lot of ways African Americans have really gotten the raw deal in the United States, and it continues. There is aggressive marketing towards African American communities in the United States. It's so good to be cool. So right, this is like in the 70s. This is when they really started like pushing cigarettes in these communities. But it continues to this day. But we notice now that he's not the only cool one. That now this one from the 90s, this woman here appears in the ad with a cigarette as well, trying to expand their base. And even today, it's being directly marketed to African American communities. So black men are 20 to 30% more likely to develop lung cancer than white men. 20 to 30% more likely. Yeah, that's disparity. Institutionalized, right there, corporatized. Okay, that's my soapbox. Recap, I talked about respiratory anatomy, ventilation, gas exchange. I talked about the miracle, the wonder, the beauty of hemoglobin saturation dynamics. Slide or two about carbon dioxide transport, and then I browbeat you into not smoking cigarettes.